Okay, so today we're going to be going over LTSpice simulations for BJT transistors. All right, so let's first start out by putting together just a simple BJT circuit. So you want to go into Draft, Components, and the BJT types are all listed as either NPN or PNPs. So NPN, NPN2, and then PNP, PNP2. Representing the PNP and NPN transistor types, respectively. So let's go ahead and construct an NPN transistor. So I'll put this down. All right, so um, like we did with the diodes, we did a pretty simple model there of just setting the forward bias. Here we're going to use a little bit more of a accurate model. So go in and switch the name from NPN to, we'll do a 3904. All right, and then let's go ahead and put that model in right away. So we go to Edit, Spice Directives, and then I'm just going to copy in a model that I've had from before. Okay, so this is a lot of information, but typically you'll find these parameters all specified for whatever NPN transistor that you're looking to use. So 38904 is a common one. It's closely related to the ones that you were using in lab, if not the exact one that you were. So dot model specifies that we're defining our own splice model. The 3904 is just a name we're giving it. And this next part here tells it that tells LTSpice that we're looking at an NPN model. And then all these other parameters go into various device level parameters that you can get from the manufacturer or obtain through measurements of the device. Okay, so click OK. We'll put that in. All right, now let's build up the rest of our circuit. So we'll put in draft component. So start with some resistors. Have RE. We'll have an RB and an RC. Okay. Let's put in our next components. So let's put in our voltage sources. Draft component. Type in voltage. That's the one we want. Okay, so we need a voltage source at our base and a voltage source up at our collector. Okay, next let's wire everything in. Okay, and then let's add in our ground. So go to draft, net name, and then, oops, common, sorry, ground. Okay, click that, and then we need one at the negative voltage source for our collector voltage supply. We need a ground for our base voltage supply, and then we're going to connect the other side of our emitter resistor to ground. All right, what else do we need? Okay, so we need to specify some values. So let's start out and let's set this at, let's say, 0.7K. Let's go 0.5K. So 500 ohms or 0.5 kilo ohms. Let's set this to 2 kilo ohms. And we'll set, usually your base resistance is pretty high, or base resistor, so let's go 100K. All right, and to start out, let's try to get the IV curve for this BJT. So instead of putting in a voltage, we're going to put in just V1 here, leave it as a variable, and we'll leave this as a variable, which we'll say V2. Okay. Next, let's label our nodes. So we need our base, our emitter, and our collector labeled. So we'll go into draft, net names, let's put down B. Our base, this way it's just easy to refer to it when we're doing our graphing. And then let's put these here and we just have to change. So this should be our collector, and down here should be our emitter. Okay, and then let's wire these up to the corresponding points on our transistor. Okay, and lastly, we need our simulation command. So draft, splice directive. So we're going to do a .dc. We're going to vary a V2, which is our collector voltage source, from 0 to, let's go up to, say, 20. And let's do small step sizes of about 0.1 volts per step. And then we're also going to vary our V1, which is our base voltage source, from 0 to 20. And let's go by steps of 2. Okay, so let's go ahead and put that down. Let's run our simulation. All right, so we have to change on the bottom here. So typically when you're doing BJT IV curves, you plot the voltage at the collector, at least for an NPN, minus the voltage at the emitter. So this would just be reversed if you're doing it for a PNP. Okay, and let's see, can we modify? All right, so we'll go from 0, 200, let's go up to 2 volts. Okay, and then for the trace, click up here. Oh, oops, no, do that. It's fine. Let's add our trace. So we want the current through our collector. So that's typically what we plot. So ICQ1. Okay, and there we go. So these are the IV curves. So each of these curves represents a different value of our voltage source V2. So when we see when V2 is 0, everything is off. So this next step would be 2 volts, 4 volts, 6 volts, 8, 10, 12, 14, 16, 18, all up to 20. So what you're doing is you're actually, in the circuit, varying how much current is flowing into the base. Since we're keeping our resistor the same, we're changing the voltage source here, so we're increasing the current flowing in to the base by increasing our voltage source V1 there. Okay, so from here you can basically determine which region you're operating in. So if you go through the math, if VCE is less than about 0.2 volts, then you're going to be in the saturation region. So this is why when we're in saturation, we put in an 0.2 voltage source between the two, between our emitter and our collector. So that's this region here where we have a sharp increase. So typically this is not where you want to run your, typically it's not where you want to run the BJT because a small change in your voltages ends up resulting in a fairly large range of currents that you can see moving through your device. So instead, typically what you want to do is have your operations somewhere here in the flat regions of the graph where you are in active mode. This being because even if your voltages vary a little bit off of where you want them to be, your current's basically going to stay the same. So your operation of your circuit is pretty tolerant to changes in the voltages. So when you're designing filters or BJT operations, again, you're typically looking to operate in the active region here. Okay. So again, this is cutoff. Flat regions are active mode, and then the regions here where the current is increasing very rapidly with small changes in VCE, that's the saturation mode. Okay, so that's how to generate IV curves for a BJT. So next, let's look at sweeping a parameter. So let's modify this a little bit. All right, so based off our IV curve, let's pick some voltages. Let's say we want to operate around, let's say 1.2 milliamps. So that means 0, 2, 4, 6, 8. We should have 8 volts for our base voltage source, and 2.4. And we'll probably put our VC about 10 volts. All right, so let's put this, change V1 to 8 volts. And let's change this to 10 volts. Might need to modify that, but it's a good start. All right, and then let's switch this R3 here to a variable RC. Okay, let's change our splice directive. Instead of doing a DC sweep, let's do a step sweep of our variable RC. And so what we're going to try to find here is at what value of RC does our BJT leave the active region and enter saturation. So how low can we go with RC before, or how high can we take RC before we leave the active region? So let's step it from 100 up to, let's say, 30K for now, and we'll go in steps of 100 ohms. So this is telling LTSpice to vary the resistor value RC from 100 ohms to 30 kilo ohms by steps of 100. So let's do that. Let's go ahead and plot. Oops, sorry, we need to add in one more analysis command, so we need the .op. Telling it to do just a basic operating point calculation here. Okay, and now what we're interested in is we want to look at RC along the bottom, so that's good. And here, what we want to look at is, so let's remove these other traces. We want to look at VB minus VC. So the voltage at our base minus the voltage at our collector. And let's get rid of this. There we go. Okay, so in order to remain in the, we should probably look at one more. Sorry, let's add in one more trace. Let's add in also VB minus VE. Okay, so first off, we can say it doesn't matter what the value of RC is. It doesn't affect our value for VBE. So that's always going to stick around 0.7 volts. And that means our base emitter junction is always going to be in forward bias. So that's what we need for the active region. But we see here that our voltage VBC, which determines whether our base collector junction is reversed to forward bias, varies pretty drastically with changes in RC. So what we're looking for is the value where we switch from saturation to active region. So that happens when our VBC is forward biased, which or our base collector junction is forward biased. And that happens when VBC is about 0.4 volts, then our collector base junction is forward biased and we enter saturation and leave the active mode. All right, so let's go ahead and add, right click. All right, so let's add a cursor. Let's quick drag it. So what we're looking for is where we hit 0.4 volts. So that looks to be somewhere between 5.3 and about 5.4 volts. 5.4 volts is a little high. So it looks like we can increase our RC value from anywhere from about 100 ohms all the way up to 5.3 kilo ohms before we leave the active region and enter saturation. And again, that's because we've flipped our collector base junction from reverse biased, where we're in the active region, to forward biased, where we're in the saturation region. Oh, okay. Okay. So that's just a quick way to start with looking at designing a circuit. We'll get more into how do you meet specific parameters when you're designing a BJT circuit in the next lecture. Okay. And that does it for this one.